Hi, I'm Viktória Fördős. I'm a Cisco NSO developer. I'm an Erlang addict. I've been active in Erlang since 2010. But before that, I will tell you in a second. But first, I think this is a very good opportunity that we get to know each other. So I have a few questions. I would like you to raise your hand if it holds for you. So, first question. Which programming language was the first you learned? Was it BASIC? Okay, a lot of hands. Was it Pascal? Wow. All right. Was it C? Okay. Was it Java? Yeah. Okay. Right. Next question. What was the first programming language you used professionally? Was it Java? Some hands in the air. Was it C or C++? Wow, a lot. All right. Was it PHP? I was a PHP developer before Erlang. Yeah. Was it Python? Some hands. Was it COBOL? No? All right. Well, last question, I promise. So, what do you use today? What is the programming language you use today? Is it Elixir? Oh, a lot of hands. Welcome, Elixir developers. Is it Erlang? Yay! Is it something else? Hello. All right. So, as we see that we are quite similar, right? We learned a lot of programming languages, but mostly imperative ones. And so, when we learn a new programming language, we compare that one to the one that we already know. This is just how our brain works. So we try to reuse the old, already proven patterns. And then, after a while, we learn to think imperatively. At least this is what I blame when I look at the first Erlang code I wrote. It's super ugly. But anyway, so let's talk about the imperative paradigm. Our old friend, we learned it, we used it a lot. It has a lot of low-level details. We describe how to execute the program. We are in full control. We focus on the how, so we describe control flow. Now, we have sequences, branching statements, loops, abstractions, all that to mutate the state of the program. Even we prove the correctness of these programs using this global system state. Check out the Horde logic, for instance. But now, I have a question. Is Erlang an imperative programming language? No, it's not. It's functional. It's part of the declarative paradigm, meaning that all lessons we learned on how to solve problems must be learned again. And then in school, we learned first that it has high abstraction level that enables us quick prototyping and testing. We learned that there is no mutable object. We get annoyed with it a bit, or at least I got annoyed with it for first. And then, so does this teach us how to write those programs? I don't think so. And then, if we are lucky, we learn about lambda calculus. We learn about functions. We learn that we can create a function, we can apply that function, we can compose those functions. We learn that everything is a value. Therefore, there is no problem passing a function as an argument to another function, right? So, and of course, we are going to learn about fixed point theorem, and we either like it or hate it, but we are going to learn about it. Anyway, the thing is that lambda calculus is the key, but it is too abstract to notice. To notice that functional programming is all about data. It is all about data. We focus on the data. We focus on the what. Now, the remember in the imperative paradigm, we were focusing on the how. Here, the how is not that relevant. It shall be seen as a black box. We just know what is our input, what is our output, and our task is to shape our data until we reach our goal. For that, we write data transformation functions. We map an input to an output. We map that output as an input to another data transformation function. We create, we apply, we compose those functions. Now I would like you to look at the function application on the slide. Now look at this sequence. They are equivalent. Maybe the sequence is easier to focus on the data. And why do I want you to focus on the data? Because then you are going to see data dependencies. And if you see that, then that gives you a natural way to see what data can be computed in parallel. Look at the data dependency graph here. Can you spot which two data can be computed in parallel? Well, it is B and C. Once the dependency, A is ready, we can compute B and C in parallel. You agree that focusing on data gives us a big benefit? I think so. So now the next question is, does Erlang likes us focusing on data? And yes, it does. It even gives us extra benefits. Great. So concurrency is built into the language. We can compute things in parallel while the data dependencies are satisfied. I would suggest that you check out the EU project called Paraphrase. They propose ready-to-use skeletons for parallel computation, for instance. We can use the Erlang processes as computational units for parallel computation. Of course, in Erlang, processes are more smart and behave like actors. But still, we can use them for parallel computation. And what about this actor thing? So an actor it shares nothing, right? It evaluates a function. And then from the external world, there comes a stimuli to what the actor is going to react. And then as a return, it may emit a signal. So from that point of view, we can see the signals, the incoming and the outgoing signals, as the input and the output of the process, which is great because now we are back to the I/O model, what we used on functions. So then we can model our processes as well. And we are going to get for free the communication protocol. Great. Now, the fact that a process is running in which Erlang VM, it usually doesn't matter until all the data dependencies are given. Location transparency, distribution are built into the language. So, but if we are in a distributed environment, then things can go wrong, right? Network glitches can occur, nodes burns down, data center melts, you name it. But then, does this mean that we need to go defensive? No. We usually do quite the opposite. We embrace failure because that allows us to focus on the happy path and on our love data. And if we do that, we are going to write code that has high abstraction level, enables quick prototyping and testing. It's easy to modify, it's easy to understand, right? And then what about the non-happy passes? Well, Erlang has a lot of fault handling methods. So you are more than welcome to use it, and you should use it. But focus on the happy path. OK, so to me, thinking in Erlang means that we focus on the data. We focus on the what. The how, that's completely irrelevant. We just know what's our input and what's our output. We write data transformation functions to shape our data. We feel the concurrency in our blood since we see data dependencies. So we do calculate things in parallel, and for that we use processes. We can scale our system horizontally, thanks to the distribution that's built into the language. And we don't go defensive. No, we embrace failure, because that allows us to focus on the happy path and on our love data. Now, I would like to show you a good example of thinking in Erlang. It is an algorithm. It is a patent. It was invented by my colleagues at Cisco. It solves a very ugly problem in scope of network management. So the algorithm is shipped with a product called Cisco NSO. Cisco NSO is a device automation platform. It's a network operating system, and it's an orchestrator. Users, through its rich northbound API, can manage virtual, physical devices, and services. Under services, we mean literally any types of services and policies, actually any rules that can be defined and feed into the network. I would like you to note that usually a service depends on multiple physical or virtual devices. So examples are virtual private networks, managing policies through access control lists, or redirecting a small percentage of your traffic to a canary deployment. All right. Now, what is the ugly problem? It is the full service lifecycle management. So the traditional way is a big lasagna. So it's a layered architecture where in the bottom you have CLI and SNMP scripts. Then on top of that, you have a big chunk of error handling, because you don't want to leave your network in an inconsistent state. So while you are propagating the changes to the network devices and something goes wrong, then you want to roll back the changes that you already made. But then what if the rollback fails? Then do you retry the rollback, or do you do another strategy? What do you do? Anyway, this layer blows up exponentially. Now, on top of that, you have the glue, the business logic. And then on the very top, you have some handcrafted northbound API. Now, in this big lasagna, you are going to implement the create, the delete, the update for every service that you want to put there. And this is time-consuming, but it's a big effort, but usually one-time effort. But what happens if I want to add one more service input parameters? What happens if the type of the service parameter has been changed? Or what happens if one of your network device has changed? Then you need to touch again all the layers, right? So this sounds a bit, it's very error prone, right? So we don't want to do it. But can we do that better? And well, there is the NSO way. So NSO needs two things to provide full service lifecycle management: create, delete, and update. Number one, it's a service model. So it is implemented in Yang, it's a modeling language. NSO sees it as a black box and uses it to store service metadata and to generate the northbound API. Second, it's a mapping from service input parameters to actual device configuration. It's a data transformation function. You only need to implement the create. So you only need to implement it in Java, Python, you name it, or provide it as an XML. It's your decision, but you only need to focus on the create scenario. So you need to implement how you would deploy your service from scratch. Now, in return, you are going to get create, delete, update. You are going to have a northbound API, and you are going to get error handling. So how is this possible? Are you ready? Here comes the patent. So it is called the TLF FASTMAP algorithm, and we are going to start with the create. So Intent arrives, and then the service parameters are given. NSO selects the user code that you implemented, and then execute the user code by providing the service input parameters and the current device configuration stored in its ACID database. So it executes the user code inside of a transaction. It captures the overall effect of executing the user code, and from that one, it calculates the minimal configuration changes that are needed to be pushed to the devices. But hey, we know where we are today. We know where we are going to be if we execute the change. So why don't we reverse that, right? We can do the reverse function there. And then that is the thing. That's called reverse diff set, and that is what we are going to put in the undo box. That's our undo information. And then the minimal configuration changes that we calculated. Now those ones we are going to push to the network, so to the physical virtual devices, in a transactional fashion, meaning that if something goes wrong during the process, NSO knows how to revert, and it is going to do that. So it tries not to leave any inconsistency in the network. What about the delete? So the intent arrives, NSO knows which service the operator wishes to delete. It picks up the undo information, calculates the minimal configuration changes that needed to be pushed to the devices, does it, again in a transactional fashion, and voila, we are done. Just please notice that there is no user code required to do the delete. And then you get a delete operation, you get the error handling, and it's amazing. Now, what about the update? So if you think about the update, it's a function composition of delete and create. And this is exactly what NSO does. So the intent arrives that we need to update that service. For instance, we need to change the, I don't know, the bandwidth in one of the legs of the VPN or so. And then NSO, in one big transaction, first runs the delete, and then on top of that, it is going to run the create with the new service input parameters. Now, it captures the overall effect of executing the two operations, the function composition. From that one, it calculates the new minimal configuration changes that needs to be pushed to the devices, and calculates the new undo information. You get update for free again. All right. Now, I have one more thing. So what if the create user code consists of multiple steps, and some of the steps are long-running and requires some communication with an external source? So for instance, allocating an IP address, or starting a new virtual device, you name it. Now, when the user code runs the create, because this is based on FASTMAP, when it runs, it is going to say that, oh, I don't have the IP address, I need to allocate that. And then it talks to the external source. And then it exits because it cannot do anything, right? And then the external source, when it is done, we expect the external source to send NSO an external stimuli, meaning that, okay, now I'm done. You have your IP address. And then NSO, like a process, takes that external stimuli, and then it is going to react to that. And then the reaction is that it again runs the update. So it cleans up again for the user code to run, and then the same user code runs again. Now, second time, the IP addresses are given, right? So the user code sees that, and then it can continue. And it does it. So this is going to be an iterative thing. So it's an update loop. And we are converging, and the network is converging to the stable state. The stable state is that the user code is done, and we deployed all the changes and pushed them to the network. You again have the northbound API, you again have the error handling, you have everything. All right. It's a very easy solution, right, to a complex problem. I think so. So what I want you to remember is what is thinking in Erlang. It is that we focus on the data. We focus on the what. Now the how, that should be secondary. We just know what's our input, what is our output. We write data transformation functions so that we shape our data and we are getting closer and closer to our goals. And we feel concurrency in our blood because we see data dependencies, and then we exploit that. So we do things in parallel, and for that we use processes. We can scale our system horizontally thanks to the distribution that's built into the language. And we don't go defensive. We embrace failure because that allows us to focus on the happy paths and on our love data. So what I hope is that next time when you have a complex problem that you would like to solve, then you will remember to this puzzle and you try to use it. And I really hope that you will get an easy solution and you will like it. Thank you.
Okay, thank you very much, Victoria. We've got time for one question if it's 3 minutes long, or 2 if they're 1.5. Anyone? Oh, we're going.
So, if you have a create in your thing and you have 12 more, and then the first one you want to undo, your undo needs to function well in a situation that's not really predictable in a sense, because so basically to make it work, you need to control it, you need to impose some constraints that this undo is not going to be invalidated because of whatever happens since the create.
Yes.
Can you give any hints on what kind of limitations or design lines you need in order for this to work?
Mm-hmm. So it is your choice to use the reactive FASTMAP or use the FASTMAP. Mm-hmm. If you know that you are going to have long-running multiple steps, mm-hmm. then you go usually with the reactive FASTMAP. But then you know that this is going to be that your system is just converging to an end state. Okay.
Anyone else?
Just a quick note. You forgot Fortran.
Thank you.
All right. Anyone else? Okay, we're going to break now in that case, and then after at 13:50, we've got Manuel Rubio who's going to be talking about PHP over Erlang. Should be enjoyable. Thank you.